Here's the assessment on acids and bases. In both of these two questions, we were looking for the most basic or the most acidic solution, but you were given different values. So I think the key is to pick one and make them all the same. So I went with pH. I'll just find the pH of all of them. And without a calculator, I just estimated. So if I knew the hydrogen concentration, then I knew the pH would be close to the opposite exponent. So in the example on the left in red, the pH would be close to 11. pH plus POH equals 14. So I was able to subtract and get a pH of 7.3 for the second one. The third one I had to do a little more work. So I estimated the POH to be about 5 and then subtracted that from 14 and got about 9. And then finally I had a pH of 4.2. So the most basic should be the highest pH. Kind of similar in the second version, I wanted the most acidic, and I changed them all to pH, but then I was looking for the lowest pH. So the first one, I would have a pH of about 10. In the second choice, I subtracted from 14 to get a pH of about 1.3. And then kind of similar with the third option, the POH would be 6, so the pH is 8. So the most acidic should be the pH of about 1.3. You would have had one of these where we were looking for the expression for Kb, which did kind of require you to write the equation. And so if they're telling me Kb, then I know that these solutions would be basic, right? So the definition of a base is a particle that removes hydrogen. And now if this is just a solution of these weak bases in water, then the hydrogen donor just becomes the water. So often nitrogen likes to act like a base. He's pretty highly electronegative. He's got an extra lone pair of electrons, so attracted to positive things like hydrogen. So we'll remove a hydrogen from water. We'll end up with a positive ion, my conjugate acid, and I should always produce hydroxide. Similar with the second option, that nitrogen would take a hydrogen from water. It'll end NH3 plus 1, and I'll still be left with hydroxide. Then the expression is products over reactants, but we do not include the water, right? Because the water would be a pure liquid. We do not include liquids or solids in our equilibrium expressions. This was one of the questions that was a bit of a stumper. And so they gave me this graph that represents the pH of a sample of water versus temperature. All right, so at 25 degrees, the pH of water is 7. That's because at 25 degrees Celsius, the hydrogen concentration, that's a plus, the hydrogen concentration is 1 times 10 to the negative 7, and so is the hydroxide. 1.0 times 10 to the negative 7. It's experimentally determined that obviously, no matter what the position of the equilibrium is, the hydrogen or hydronium and hydroxide will always shift in the same ratio. So whether I'm shifting more forward or more reverse, the hydrogen or hydronium and hydroxide will always be at a 1-to-1 ratio. At 25 degrees, it's 10 to the negative 7th moles per liter, which is why the pH is 7. The POH would also be 7 at 25 degrees. And that's where we get pH plus POH equals 14 at 25 degrees. But no matter what the temperature is, hydrogen or hydronium and hydroxide will always be the same. Now, if I look at increasing the temperature and I see that the pH is going down, that must mean that there's more hydrogen in the solution. This is an endothermic process. Because if I increase the temperature, that's like adding energy, and that would shift it more forward. So that I'm getting more hydrogen or more hydronium. Yeah, that's why my pH goes down. pH is opposite log of the hydrogen or hydronium concentration. So if I think about like if the pH is 6.4, the hydrogen concentration is 10 to the negative 6.4, which is a greater amount of hydrogen than 10 to the negative 7th moles per liter. But what we got to think about is this, that if I'm shifting it more forward, hydrogen and hydroxide will always be the same concentration. So that if you take pH opposite log of the hydrogen concentration, or pOH opposite log of the hydroxide, they should always be the same. Oh, isn't that interesting? So the pH graph would look exactly, I should say the pOH graph looks just like the pH graph. Ah. Now, if I'm looking at like hydrogen plus hydroxide equals 14, maybe then if I'm thinking about an acid, well, an acid is going to have more hydrogen, less hydroxide. Or a base has more hydroxide, less hydrogen. And then those two change in opposite ways. If it's more acidic, then the pH is lower and the pOH is different. But this isn't an acid or a base, it's water, where the hydrogen and hydroxide are the same. That would not be the case if the solution were an acid or a base. And I think that's maybe what stumped some of us, that we were kind of thinking that the pH plus pOH had to equal 14, so that like if my pH is 6.4, then my pOH has to be greater. So if they add up to 14, that would be true if it were like a solution that was acidic or basic, that has extra hydrogen or hydroxide. But with water, they'll always be the same, whether I shift more forward or more reverse. There's always the same amount of hydrogen and hydroxide, so the pH and pOH of water will always be the same. Tricky, huh? This one was fine. Rank these monoprotic acids from weakest to strongest. All right, well, I do see that there is one that has a lower pH. So like in the example on, I guess both of them, there is one solution that has a noticeably lower pH, which would mean more hydrogen, and it's coming from a solution with a really small molarity. So it's the smallest concentration, but yet it's giving me the most hydrogen. It's the most acidic solution. So right there then, I know the strongest acid in the example on the left must be HX, and the sample on the right must be HY. Maybe that's a good place to start, that this guy must be the strongest, and this guy is the strongest. From there, I've got two solutions that are obviously less acidic, a pH of 3 or a pH of about 4. And so they have about the same amount of hydrogen, like a 4.1, a 4.2, they have about the same amount of hydrogen. Or in the second example, both have a pH of 3. But one of the solutions is more concentrated. So if they have the same amount of hydrogen, these guys are approximately the same hydrogen concentration. And same thing could be said about these guys. There we go, we'll just do that. They have the same pH, so they have the exact amount of hydrogen. But one of them had to be more concentrated in order to get that amount of hydrogen. So that must be the weaker acid. So the weaker acid, and the weakest acid, is the one that's the most concentrated, but then it's giving me the higher pH. And so in the example on the left, it would be the HY that must have been the weakest. And on the right, it must be HZ that was the weakest. Most of us didn't have a problem finding the one that was the strongest. From there, we had to kind of rank the other two. Approximately the same amount of hydrogen if the pH is the same, but one of them had to be more concentrated in order to get that amount of hydrogen, which meant that it didn't fully dissociate. In these two examples, we were given a pH, and we wanted to calculate the Ka. And magically, you can do this without a calculator. The trick is that we have to remember that if we know the pH, we know the amount of hydrogen in the solution. And that's the amount of hydrogen at equilibrium. So I set up these ice tables with some random weak acid. I just called it HA. So I set up a real generic equation for a weak acid in solution. I had the initial molarity. Initially, the two product ions would be 0. And now I do know the amount of hydrogen at equilibrium because I know the final pH of the solution. So what's in blue is what I knew, but then I was able to fill in the rest of the table in red by kind of backtracking. So if I knew one of the equilibrium conditions, I do know my change. Everybody shifted forward by 10 to the negative third moles per liter or 10 to the negative fifth moles per liter. Now eventually when I set up my ice table, I've got my two products, so like 10 to the negative third times 10 to the negative third over my reactant. But because I don't have a calculator, I just figured, if I've got 0.1 and I'm subtracting 0.003, that's pretty small. So I just kind of made an assumption that in the denominator, I'm just going to use 0.1. If I were calculating the Ka, obviously then I could plug it all in, but sometimes we would kind of ignore that x anyway, if x is going to be something small. So now I can say, all right, 10 to the negative third times 10 to the negative third is 10 to the negative sixth divided by like 10 to the negative first, which would give me 10 to the negative fifth. Or in this second example, I'd have 10 to the negative fifth squared, or 10 to the negative 10th, divided by approximately 1. Subtracting 10 to the negative fifth is a really small number and probably insignificant. Similar, we can calculate the Ka if I know the percent ionization. That's another way of telling you X. So in each situation, we knew the molarity of the original weak acid, and then we could just multiply that by the percent ionization. We just have to use it as a decimal. It's like saying 5% of that 1 molar solution will dissociate, or 1% of that 2 molar solution will dissociate or ionize. That's your shift. That's the amount that shifts forward. So again, I could kind of set up my ice table with the initial molarity of the acid. The two product ions are initially 0. And then I know my shift, 0.05 or 0.02 moles per liter. So I kind of did something similar that if I don't have a calculator, I got to try to make this calculation somewhat manageable. And again, both X values, 0.05, 0.02, they're relatively small. So without a calculator, I just ignored them and said, all right, and with a calculator, obviously I would say like 0.05 times 0.05 divided by 0.95. But without a calculator, I just assumed it was about 1. So I had 5 times 5, which is like 25, times 10 to the negative fourth, or 2.5 times 10 to the negative fourth, divided by approximately 1. And in the second example, I had about 2 times 10 to the negative second, or 0.02, times 0.02, or 2 times 10 to the negative second divided by 2. So about 4 times 10 to the negative fourth divided by 2 gives me 2 times 10 to the negative fourth. Fantastic. So 2 different ways of showing us x, either by giving us an equilibrium amount, which I could get by using pH, or by telling me the amount that shifts forward, the percent ionization. 7 was missed a little bit. Which of the following salts is the most basic? Well, hopefully you didn't pick the sodium chloride, because that one's neutral, right? All right, so then I decided to kind of estimate the Kb values. I'll figure out like which one's got the highest Kb. And I did have to kind of think about what it means to be Ka1, Ka2, Ka3. When you've got more than one hydrogen, each hydrogen comes off one at a time, and they have their own Ka values. So Ka1 for phosphoric acid would be after the loss of one hydrogen. So the ion left in the solution, the negative ion, would be H2PO4. So obviously we'd produce a hydrogen, and I'd be left with H2PO4 minus. Then I would produce another hydrogen, and I'd be left with HPO4 minus 2. And finally, after the third hydrogen, I'd be left with the PO4 minus 3, which was in the first option, sodium phosphate. So I used the third Ka, because that's the one that'll be in reference to the formation of phosphate. But then I just kind of estimated the Kb. I said, well, if Ka is 10 to the negative 13th, Kb is like 10 to the negative 1st. And then I kind of did the same thing with the carbonic acid. Ka1 would be after we lose the first hydrogen, so I would be left with hydrogen carbonate. The Ka2 would just be for carbonate, CO3 minus 2. And so kind of similar, if the Ka was 10 to the negative 7th, well, then the Kb is probably about 10 to the negative 7. And the third choice, ammonium NH4 is acidic. That's the conjugate acid of the weak base ammonia NH3. So hopefully then it was like a 50-50 choice, right? That this guy should be mildly acidic, and this one is neutral. So between the first two, I picked the one with the higher Kb. And finally, you could use a calculator to determine the pH of a weak acid. Once you do a few of these weak acid calculations, they're all really similar. All of the equations would involve the weak acid in solution with water. So the acid is the hydrogen donor, and the water will be the hydrogen acceptor. So I'll form the conjugate base and H3O hydronium. I've got the initial molarity. The two ions on the product side would initially be 0, but this time we have no indication on how far forward we should shift. This is when we can call it X. When you shift everybody by X, look what happens in your ice table. I mean, it's always that the products are both X, and the reactant becomes your concentration minus X. So both of them will have like X squared over the molarity minus X. And because both of the Ka values are small, and by small we just mean less than 1, X should also come out to be something small. So I can ignore the minus X, and then all I have to do is cross multiply and take the square root. And then we got it. We got the pH. Now, of course, you can look for things like a pH of 0.6. That doesn't really make sense because this is a weak acid and its molarity is not that concentrated, like 0.25, 0.15. It would take a really high molarity in order to get a pH of like 0.6 from a weak acid. Like in the second one, a pH of 10.1, that's a little unrealistic too, because it is an acid, even though it's a really weak acid. I shouldn't have a pH that's above 7.